Let us now discuss about Kirchoffs law. Consider a large isothermal enclosure of surface temperature Ts. So you can see here we have considered a large enclosure here and its surface temperature is Ts, within which several small bodies are confined. So you can see we have considered three bodies here, A1, A2 and A3. So there can be many more than three bodies. Since these bodies are small relative to the enclosure, they have negligible influence on the radiation field, which is due to the cumulative effect of emission and reflection by the enclosure surface. So now what's happening actually, see this cavity is behaving as a black body actually, and whatever will be the energy emitted by it, this may be following, say here at this particular point, and there could be reflection also, but that reflection will also be absorbed when it falls somewhere else on the same body. And because uh, these bodies, the considered bodies, the small bodies A1, A2 and A3 are very small, we are not worried about that these uh, reflections are actually uh, it's falling on these bodies actually. It's because being very small. Recall that regardless of its radiative properties, such a surface forms a black body cavity. So cavity itself is forming a black body. It is behaving as a black body. Now, what is the implication of this cavity to behave as a black body? Regardless of the orientation, the irradiation G, that means the energy falling by experienced by any body in the cavity is diffuse. So, for example, if I consider about body A1, so body A1, certain amount of the energy, if it falls on this body A1, that would be considered as diffuse. Means its intensity of the irradiation will be same from all the directions actually, and equal to the emission from a black body EB at Ts. So basically, whatever will be the energy EB which is being emitted by the cavity, that would be equal to the irradiation. Okay, that would be equal to the irradiation. So G is actually equal to EB. So that is the major implication of a black body cavity or a uh, cavity actually, because cavity will always behave as a black surface. Now, under steady conditions, thermal equilibrium must exist between the bodies and the enclosure. So, because there is continuous emission from the black body cavity, and there is a part of it may be falling on the surface A1, A2 or A3. So naturally some sort of thermal equilibrium must exist after a certain period of time between the bodies and the enclosure. So hence we can say that temperature T1, which is the temperature of the body A1, is equal to temperature T2, and that should be equal to temperature T3. And what will happen? The net rate of energy transfer to the each surface must be zero, because there is certain energy which is falling on the surface, and the surface is also emitting certain amount of the energy. You can see this here. G is the energy falling on the surface A1, and E1 is the emission of this surface A1. So net rate of energy transfer to each surface must be zero actually, because all the bodies are under thermal equilibrium, because they are following this condition that temperature is same for all the bodies as well as the cavity. So we can apply the energy balance to the control surface about body 1, and it follows. Now suppose G is the energy falling on this body A1. So what will be the total energy which will be absorbed by the body A1? That would be equal to alpha 1 into G into A1. Okay, because the unit for G is watt per meter square, we have multiplied by the area, and alpha shows the absorptivity of the body 1 minus what is the emission from this body A1, that is equal to E1. Once again its unit will be equal to watt per meter square, so we have multiplied by the area of this body, and we are considering this emission is at the temperature of the cavity itself, or the temperature T1, and it should be equal to 0 because net energy transfer is equal to 0. Now we have just said that the value of G is equal to EB. G is irradiation which are falling on the surface, and EB is the black body radiation. So I can replace G in this particular equation. So what I will do, I will erase this. So I will remove this G by this value of EB. So I get alpha 1 EB TS is equal to E1, which is a function of TS, and A1 and E1 cancels out from this particular equation, and then I can say E1 by E alpha 1. This has been brought on this side. So E1 by alpha 1 is equal to EB. So similar equation can be written for the other surfaces also. So you can see it here. This result must apply to each of the confined bodies. Then we obtain E1 by alpha 1 corresponding to Ts, E2 by alpha 2 corresponding to Ts. So these are equal, and that should be equal to EB. So you can see here how EB comes. You can see this particular equation. Okay, this is how the EB comes into picture. This relation is actually known as Kirchoffs law. That means the emissive power of a surface divided by its absorptivity should be equal to the emissive power of the black surface. And a major implication is that since the value of alpha is always either less than or maximum equal to 1, in that particular case, E, which is the emission from the surface, will be equal to emission from the black body or less than the emission from the black body. So this sign shows this particular thing. Hence, no real surface can have emissive power exceeding that of a black surface at the same temperature, and the notion of the black body as an ideal emitter is confirmed here. Now, let us once again see the definition of total hemispherical emissivity. And if we are using this definition of the total hemispherical emissivity, an alternative form of the Kirchoff law can be defined. So you can see it here, E1 by alpha is equal to E2 by alpha is equal to EB. This is what we have said is the Kirchoff's law. So what I can do is I can write this as E1 divided by EB is equal to alpha 1, and E2 divided by EB is equal to alpha 2, and so on I can write. So if I take this particular equation, what does it shows? It shows that emissivity is equal to E by EB, E by EB. Or I can, in a different fashion, I can write it as, if you see this particular equation, and from here, if you divide the each equation by EB on the left hand side, if you forget about this, you divide both sides by EB then. Okay, I am saying that here it is E1 divided by alpha 1 divided by EB is equal to E2 divided by alpha 2 EB is equal to dash dash dash, which is equal to EB divided by EB. So you can see here this value E1 by EB is now equal to epsilon 1 divided by alpha 1 is equal to epsilon 2 divided by alpha 2, and that should be equal to 1. Hence, for any surface in an enclosure, epsilon is equal to alpha, or emissivity is equal to absorptivity. That is, total hemispherical emissivity of the surface is equal to its total hemispherical absorptivity. And what is the validity for this? The surface irradiation has been assumed to correspond to the emission from a black body at the same temperature as the surface. This we have already considered, because we have considered a cavity here, and then we have considered the surfaces. We have said that the surface temperature and the cavity temperature is same, and the cavity is behaving as a uh, uh, basically as a emission from a black body. Now this preceding derivation may be repeated for the spectral conditions also, and for any surface in the enclosure, it follows that epsilon lambda is equal to alpha lambda. This we have already proved here. You can see it here. Alpha is equal to emissivity. So this can also be proved that epsilon lambda means spectral emissivity is equal to spectral absorptivity. This equation is applicable if the irradiation is diffuse or if the surface is diffuse. So if the surface is diffuse, that means it will be emitting the same amount of the energy in all the directions. Or if the irradiation is diffuse, irradiation means any irradiation which is falling on this surface, or diffuse means in all directions, from all the directions, the same amount of the energy is falling on this surface actually. Okay, so that is the meaning here. A form of the Kirchoffs law for which there are no restrictions and involves that is basically that involves the spectral directional properties. That means epsilon lambda theta is equal to alpha lambda theta. So what is epsilon lambda theta? Epsilon lambda theta is spectral directional emissivity. Alpha lambda theta is spectral directional absorptivity. So that can also be proved to be equal, because this is also applicable because epsilon lambda theta and alpha lambda theta are inherent surface properties. That is, respectively, they are independent of the spectral and directional distribution of the emitted and the incident radiations. So basically, epsilon lambda theta and alpha lambda theta are the properties of the surface actually.